Hello, my name is Blake Schramm, and along with my teammates Levi, Adam, Lucas, and Yassine, we developed an automated testing device for Bradford White Corporation as our senior project. The problem we were tasked with was to create an automated testing device that runs quality assurance testing on the system software for the Aerotherm G2 water heater via interacting with the user interface. The goal of this automated testing device was to reduce the time required for quality assurance testing, lowering overall testing costs while enabling testing under actual water heater operating conditions, which the current testing method does not replicate. The current testing method uses soldered wires connected directly to the water heater buttons. The Pickering test chassis is then used to simulate water heater operation while a 4K webcam captures the display information. The entire test sequence is controlled through LabVIEW. Although this method works, it has several disadvantages. It is time-consuming to set up, difficult to move between locations, and requires modifying the water heater, making it destructive testing. To address these issues, our design needed to meet several key requirements. It needed to weigh less than 20 pounds to remain portable, apply between 1.5 and 4 pounds of force to reliably press the user interface buttons without causing damage, achieve greater than 95% OCR accuracy, maintain less than 1/8 of an inch of deflection under a 5-pound external force, and interface with the existing LabVIEW testing software. Our automated testing device consists of 4 primary subsystems: the mounting system, button press system, vision system, and the electronics and control system. Together, these subsystems allow the device to mount to the water heater, interact with the user interface, read the display, and communicate with the host computer. The mounting system was designed to securely attach the device while remaining completely non-destructive. Magnets serve as the primary mounting method, allowing the device to be installed and removed quickly. The geometry of the housing creates an edge clamping effect that precisely aligns the internal components with the water heater interface. Finally, a Velcro strap provides additional retention, ensuring the device remains secure throughout testing. The button press system uses 7 individual servos, one dedicated to each button on the water heater interface. Each servo drives a custom linkage that converts rotational motion into linear motion needed to press a button. Springs were incorporated into the linkage design to provide a more consistent pressing force, and each servo can be individually calibrated to compensate for manufacturing tolerances and ensure reliable operation. To verify the results of each button press, the device includes a vision subsystem. The Raspberry Pi Camera Module 3 captures images of the water heater display. These images are first processed using OpenCV to improve image quality and isolate the display. The processed image is then passed to Rapid OCR, which converts the displayed text into machine-readable data. This information is ultimately returned to the host computer for evaluation. The electronics and controls subsystem serves as the brain of the entire device. A Raspberry Pi 5 coordinates all system operation, while an Adafruit 16-channel PWM Pi-Hat provides the additional PWM outputs needed to control the 7 servos. The system is powered by a Meanwell 5-volt power supply, which is enclosed within a 3D printed cover to eliminate electrical shock hazards. The software running on the Raspberry Pi receives commands from the LabVIEW host computer. It recognizes 3 primary commands: button press commands, OCR requests, and system shutdown commands. Each command triggers the appropriate software routine, while an integrated error handler detects and manages unexpected states to improve reliability. This video demonstrates the completed system performing an automated quality assurance test. The LabVIEW program begins by sending test commands to the Raspberry Pi over Ethernet. The Raspberry Pi actuates the appropriate servo through the PWM driver, causing the linkage to press the selected button on the water heater. After the display updates, the camera captures an image, OCR processes the displayed information, and the results are transmitted back to LabVIEW, where each field is verified and reported as either a pass or a fail.
Go for it.
side of the slide, LabVIEW displays the result of each individual test. Software compares the OCR output to the expected values for fields such as operating mode, temperature, information line, time, date, and display icons. Each item is then either marked as a pass or fail. In this demonstration, every field passes successfully, indicating that the user interface is functioning as expected. In development, we encountered several engineering challenges. Variations in button press force were addressed by incorporating springs into the linkage system. Servo positioning was improved through a custom calibration script. OCR accuracy was increased by implementing image preprocessing techniques. And reliable communication between LabVIEW and Raspberry Pi was achieved through a custom TCP/IP communication protocol. In conclusion, our team successfully developed a portable, non-destructive automated testing device capable of interacting directly with the Aerotherm G2 water heater. The completed system reduces setup time, eliminates permanent modifications to the unit, and enables testing under actual operating conditions while integrating seamlessly with the existing LabVIEW testing software. Finally, we would like to thank Bradford White Corporation for making this project possible and giving us the opportunity to work on a meaningful real-world engineering challenge. We would also like to thank our GVSU faculty advisors for the guidance, encouragement, and support throughout this project. Thank you for your time and for watching our presentation.